Okay, so now is 6.1, and it's a really long title, so I'm not going to write it. But it's called Solving Systems of Linear Equations Using Matrices. The word matrices, plural is like that, but singular is matrix. So some of you may have seen or heard that word, and some of you may have even worked these problems before. Uh, but what I don't like about this section is that it's assuming that you know something from chapter 5.1. And it's not part of our required material learning to go over 5.1, but I'm going to go back and show one example from 5.1 because it's very useful to understanding where the matrices came from. Um, Otherwise, it just seems kind of like a convoluted mess, and it'll still seem like that at the first until you get the hang of it. But I think showing 5.1 kind of helps you understand why we're doing what we're doing with matrices. And what 5.1 is we're solving systems of linear equations. But here in 6.1 they add on using matrices to solve them. So let's look at 5.1 real quick, and then we'll get back to 6.1. So 5.1, and this is just an example. I'm gonna say example 1, and just a heads up, this 6.1 this section 6.1 is going to be very long problems, and it's going to take up a lot of board. So I'm going to do my best to show you how to do it up here, but I'm going to have to erase a few times. Just please bear with me while I'm doing that. So example 1 from section 5.1, solve this system of equations. We're going to say x plus y equals 6 and negative 3x plus y equals 2. So this is what it means to have a system of equations, or system of linear equations. You have two equations. You have more than one equation that are linear, and you want to solve for x and y such that both of these equations are true. When you add x and y together, you get 6, and when you use those same x and y values, you get 2 on this equation. So you can make some guesses on this one, especially this one here. You could say 0 and 6, 1 and 5, 3 and 3, and then 4 and 2, and 5 and 1, and 6 and 0. But then you also have to make sure that they match here. And this is a very simple example. That's why we can kind of guess and check and kind of figure this one out. But I actually want to go through the process of how you do this by hand, and then I'm going to show you the process of how we would do it using matrices, which matrices is our end goal. What I'm showing you here is just to kind of connect the dots between matrices and what we were supposed to do in chapter 5.1. All right, and actually what I'm going to do, I'm going to use the same problem. I'm just going to rewrite it just because my board is kind of limiting me how I would like to write it, but you should be fine on your paper. Solve x plus y equals 6 minus 3x plus y equals 2. Alright, so to solve this, first you would take either one of these equations and you would solve one of them for x or y, whichever variable you wanted. So what I'm going to do is I'm just going to take the top equation, and I'm going to rewrite that as I'm going to get y by itself. So I'm going to subtract x from both sides on this top equation. So when I do that, I get y equals 6 minus x. And you could solve for x instead here and then work the problem the same way, and you'd get the same answer. But just for simplicity's sake, I'm just going to do this one. So now this top equation is rewritten as this. So it's the same system of equations. We have this equation and this equation now. What I can do is I can take, now that I know this y is equal to 6 minus x, I can take this whole thing and plug it in here for that y. So y is equal to 6 minus x. So anywhere in this equation where there's a y, I can replace it with 6 minus x. Alright, so Now this minus 3x and then plus y, but I just told you y is equal to 6 minus x. So now this is 6 minus x is equal to 2. Alright, so this y was equal to that 6 minus x, which is what I just said over there. And now, if you see what that lets us do or have, is now we have a single equation in terms of one variable. It's x. So now we just get x by itself, and out will pop our x value. Alright, and these parentheses here is probably a good habit to get into, but in this particular problem, they don't do anything because there's no minus sign or anything to distribute. So minus 3x, and so I'm just not going to write them. It's okay if you did. But minus 3x minus x is minus 4x plus 6 is equal to 2. In getting x by itself, I subtract 6 from both sides. And so that gives me minus 4. And divide both sides by 4. So you get x is equal to 1. Alright? Which is very helpful to know. Why is it helpful to know? I would like you to pause the video and try to solve for y. Figure out what y is. If you're struggling, don't take too long of your time, but it's worth a shot to try for you to try to figure it out. Okay, but here, so we know x is equal to 1. So all we have to do is plug it into one of the two original equations and then solve for x. So what I'm going to do is, and some of you may see a different way to do it right now, and that's perfectly fine. But what I'm going to suggest is that you always go back to the original equations and plug it into one of them. I'm just going to plug it into the top. X plus y is equal to 6. What did we say? What did we say x was just equal to? We just found x to be 1. So we replace x with 1. That's plus y is equal to 6. And then subtract 1 from both sides. So y is equal to 5. And this x equal 1 and y equal 5 would be your answer. And if you want to check yourself, you take this x equal 1 and y equal 5 and you plug it into both of these equations, and the top one will equal 6 and the bottom one will equal 2. So what is this doing for us? Why does this even matter? What does this x equal 1 and y equal 5 mean to us? Well, what it means is it's taking these two equations and it's seeing where they're both satisfied. Graphically, what that looks like, it looks like the intersection of those two lines. So this particular line could be going like this, down, and this other graph could be going like this, and that particular point of intersection is where this x equal 1 and y equal 5 comes into play. And that's what solving systems of linear equations is about. It's finding that intersection point, and that's what matrices are going to let us do. Now, if you don't know what a matrix is, I'm going to show you right now how we would write a matrix. You start off, and before we get into the full-blown problems, I'm going to do a lot of intermediate steps here. But there is a process of how we're going to solve all of these. But for now, I'm just going to introduce what a matrix looks like. So a matrix, when we start writing them, it looks like you have brackets like this and a line right there. Okay, and I'm going to use this example here to populate my matrix. All right, so let's see. Let's start with, so this line here, that's basically our equal sign in a matrix. So you come over here to these two equations, and the equal sign is here. So we would populate on the right side of that equal sign with a 6 and a 2. All right, and then we have other numbers that are going to go here and here, and those are simply the coefficients of each of these. All right, so the coefficient here is, there's nothing written, so that means it's 1. The coefficient here is 1 also. Alright, and then the coefficient, we go to the next equation, excuse me. The coefficient here on this x value is -3, and the coefficient here on this y is 1. So if you notice, what we have to have when we're writing these is you have to have the x's on top of each other, the y's on top of each other, and the answers all by themselves on top of each other. And eventually we're going to find out that there's more variables. You're going to have a z column, so you just have to make sure everything's lined up. And then when you bring it over here to the matrix, you have to make sure everything's lined up. So notice this is the coefficient here is 1, 1, and 6. 1, 1, and 6. And then -3, 1, and 2. -3, 1, and 2. So each row represents an equation. Okay, so that's how we would set up a matrix to begin. And then, so at this point here, we are in the same position if we started here and here. And then you have to do all of this work to find the answers. And so we have to do all this work, and then we'll wind up with the same answers. The in-between steps I'm going to go over in the next few examples, slowly leading you into how to do them, because it can get tricky. So for now, I just want to show you what the beginning looks like, which is this, and then I'm going to put some dots here and say work, and just to represent the work in the middle. But I'm going to show you what the beginning and ending looks like on a matrix. So what we want to happen in the end is we want to have our diagonal 1 right here, and then everything else are zeros. And then out here will be our final answers. Alright, so the end goal of a matrix is to have a diagonal 1 and everything else zeros. And then what's out here will be our answers. So, and I'll get to how to do the work in a minute. Now this is a 2x2 matrix. You will most likely have a 3x3 matrix on the exam. Just to show you what the end result on a 3x3 matrix will look like, it's just adding another row and column here. So you would have 1, 0, 0, and then some value here, 0, 1, 0, 0, 0, 1. And notice it forms that diagonal 1 and everything else is zeros. And then this can get bigger and bigger to 4x4, 5x5, a million by a million. And in fact, this is a really well-known, well-used techniques in all kinds of real-life examples. Google uses matrices, and there's all kinds of real-world applications of matrices, and I encourage you to look for those. Alright, so you know how to set up a matrix now. You know what we're looking for in the end. And now I want to begin by showing you the steps in between, the work part. And so the best way to do that is just to show you some kind of just to show you some examples. And these won't be examples where I'm necessarily working through the entire problem, but there are 3 main operations that we can do to a matrix, and the point of these next 3 examples is just to show you those 3 operations, and they're not necessarily have to go in this order every time. In a couple examples, I'll start telling you a process of you need to do this first, this next, and then this next. But as of right now, I just want to get these operations to you. So these are called elementary row operations. Row operations. That says operations. Alright, number 1. And this one is very helpful, especially in the beginning of problems. But they can be used in the middle somewhere. But so this first one is called interchange 2 rows. And let's use this as our example. Let's say we have -3. No, I lied. I didn't write my notes how I wanted it. -10, -15, -20. 1, 2, and 5. And so this is just a 2 by 2 matrix. And when I say 2 by 2, I'm not counting, don't get confused, I'm not counting the equal side portion. When I say 2 by 2, it's only this part here. All right. So like I said, I'm going to run out of room on this, and I'm going to try to do my best to make this as least confusing as possible. But interchange 2 rows is helpful. And it's the most helpful usually in the beginning, because what we're looking for is to get that diagonal 1. And we're gonna talk about the diagonal 1 a lot. So I want to make this spot a 1 and this a 1 eventually. So the way you always start a matrix, you know how to set it up and start, and then the next step is to make this top left entry a 1. And the easiest way to do that is if there is somehow we could take this 1 and just move it up here. And what you can do is you can take the entire row, so this 1, 2, and 5, and you can switch row 1 and row 2, so interchange them. So all of these numbers on row 1 move down here to row 2, and all the numbers on row 2 move up to row 1. All right. So if I had a better board system here, this would be a little more clear. But so this is the matrix I'm currently on, and then you're always going to have a long arrow. And in between the long arrow, on this side of the long arrow, I'm going to write my new matrix after I do my operation. So if I didn't have this gap here, this arrow would basically be almost touching that matrix. But the gist of it is you have your starting matrix, and then you have your long arrow, and then this is the new matrix you're going to. And on top of this long arrow, we're going to write what operation we're performing. So that tells the reader, in particular me or yourself, what operation I'm doing from here to here. And so what I said I was going to do is interchange 2 rows. And the way you write that is you take row 1. That's how you represent the top row, row 1. Row 1 is this -10, -15, -20. And you want to interchange, and it's the big, I guess, bold double arrow we've seen a couple times. So this means interchange. So row 1 interchange with row 2. And row 2 is the second row down. This entire entry is row 2. And then you have row 3, row 4, row 5, and so on. So what this is telling you is it's saying interchange row 1 and row 2. Just flip them. So now my row 1 up here is my row 2 over here. You're just interchanging them. Flipping position. And that is all you have to do for interchange row 1 with row 2. Alright, the second row operation, I'm going to try to squeeze it in here on the bottom, is multiply a row by a non-zero constant. Multiply a row by a non-zero constant. And today I'm going to try to just use this as one consecutive board. Okay, so the starting matrix, let's start with, what I want to do is actually want to start with the one we just finished here. So this matrix, I'm just rewriting it over here. 1, 2, 5, -10, -15, and -20. And now I want to perform a row operation. So what do I have to do if I'm going to perform a row operation? I have to have a big arrow here pointing to the new matrix, and on top I have to write my operation that I'm performing. Alright, so my operation that I'm going to perform, well, here's what my matrix at the end, just to get it out of the way. So, and this may not be particular, this may not be the particular, this may not be a particular problem that we'll come across in a real example, but this is just to get across one of the row operations. So I may not, but anyways, so to get this row operation across to you, notice row 2. What does row 2 have in common? It has a 5 in common. It has a negative 5 in common. So we could take out one of those. And it doesn't matter which one. Just for the sake of the next example I'm going to show you, I'm going to just take out a 5. And I really should take out a negative 5, but again, just to make my next problem a little clearer, I'm going to stay away from that for right now. So what I want to do is I want to multiply, and remember this says multiply a row by a non-zero constant. So that means I can multiply any row by 1, which wouldn't really do anything for us, but I can multiply a row by 2, 3, 4, 10, 100, 1,000, negative 1,000, negative 8. I can multiply it by 2.7 or negative 9.3. I could even do it by a fraction, say 1/2 or 1/5. And in this case, if I multiply this entire row by 1/5, then that will make this a 2, a 3, and a 4. And let me just show you. It's a little confusing at first, but the more you do these, you'll catch on. So what I want to do is I want to multiply, which row is this one? This is row 2. And I want to multiply it by 1/5. And this is a part you have to remember to do. You want to say that gives me, so you draw another little arrow, that gives me a new row 2. I messed up that little arrow. Another arrow, and say that it's going to give me a new row 2. So as long as you multiply that 1/5 to every number in row 2, that's going to give me a new row 2. Alright, I know it's confusing, just bear with me and we're going to work more examples. So over here on the matrix I'm performing the operation to, what's not changing in this matrix? The row 1 isn't. 1, 2, and 5. So I'm just going to go ahead and write what's not changing so I can get it out of the way. Now I know row 2 is changing. So I'm taking 1/5 times row 2, and that's what I'm placing in the new row 2 over here. So 1/5 times negative 10 is negative 2. Try again. And then you move on to the next entry. 1/5 times negative 15, that's negative 15 over 5, which is negative 3. And then move on to the next entry. 1/5 times negative 20, which means negative 20 divided by 5 is negative 4. Okay, so that's multiplying a row by a non-zero constant. I'm going to leave this bottom one on here because I'm going to use it in the next example. Alright, so the third and final operation that we can use is add a multiple of one row to another row. Add a multiple of one row to another row. And this is just an extension of part 2. So now we can multiply a row by any non-zero constant, and then we can add another row to it, giving us another new row. And let me show you what I mean exactly. So let's start with this example here. We have 1, 2, 5, negative 2, negative 3, and negative 4. And I got my big arrow. And so now, let's think about, now I'm going to tell you the next step into solving a matrix. So the first step is obviously setting up the matrix. The next step was to get a 1 in the top left corner, which we did. And then once you get a 1 in the top left corner, you want to make all the entries below that 1 a 0. So the only entry below this 1 is this negative 2. So we have to make this negative 2 a 0 somehow. All right. And the way we can do that is by multiplying this first row by 2, a positive 2, and adding it to row 2. So let me say that again. The way we make this negative 2 a 0 is by multiplying row 1 by 2, because 2 times this 1 gives us a positive 2. And then you add it to negative 2 gives us a 0. Alright, let's try. So the way you would write that is, I want to say 2 times row 1. So I'm multiplying row 1 times 2. And then I'm going to add it to row 2. And I'm just going to make it a little clearer. Kind of wrote it weird. And then that implies a new row 2. And so these steps I'm doing are very similar to that very first example. They're just written a different way. And we do it this way because once you get into bigger problems and more variables, such as 100 by 100 matrices, this becomes very easy compared to the first example I showed you. Alright, so my new matrix is going to be this. So let's always start by writing the row or rows that are not changing. So the row that's changing here is row 2. So row 1 isn't changing, so I'm going to just rewrite it. Get it out of the way. Makes our life a little easier. Now we only have to focus on row 2. Alright, so I'm going to do a little side work here. And the side work I'm just going to write somewhere in here. So follow along with me, maybe watch this the first time, rewind it, and write it as I do it the second time. So what I'm going to do is I'm just going to read this operation, and I'm going to write it as I do it. So 2 times row 1 plus row 2. So 2 times row 1, which is a 1 in this case. So start with this entry, and then you just keep moving on. 2 times row 1, so 2 times 1 is 2. And then you're adding that to row 2. And the entry here is negative 2. So 2 plus a negative 2 gives you 0. And that is what your new row 2 is. Alright, and again, just take it slow, take some time, you'll get it, I promise. Just, you have to keep working. Alright, now move on to the next entry. 2 times row 1, so 2 times 2 is 4, and then plus row 2, which is negative 3. Then 4 plus negative 3 is a 1. And that's your new row 2 entry. Alright. And then 2 times row 1 plus row 2. 2 times row 1. So 2 times 5 is 10. Add to row 2, which is negative 4. Add down gives you 6. Alright. And that would be our updated matrix. Alright, and this part right here in purple is just my work, and I may not do this every single time. I'm just doing it right now so you can see the numbers, so you can get the hang of what's going on, and I encourage you to do this step every single time if you need to. I'm going to do it a couple times, and then towards the end of the video I'll probably stop doing it in my head. So just bear that in mind. Okay, so next I want to talk about this how questions will be worded and what they'll be looking for at the end of each problem. And there's two different ways to end one of these problems, but they wind up with the same answer. And there's one way I prefer over the other. In some cases, the other way might be better. But for what we're doing, I'm going to show you both ways, but on the exam, I will probably let you choose which way you want to do it. So you have, let's see here, you have something called Gaussian elimination. And I'll write that up here, don't worry. Gaussian elimination. And what it says, you do the matrix work exactly the same, except when you get to the end. When you get to the end, the ending changes between the two eliminations I'm going to show you. So when you're using Gaussian elimination, you get a diagonal 1 with a 0. Let's do a 3 by 3. It makes it easier. There's your diagonal 1, 0, 0, 0. With, I'm just going to make up some letters here, A, B, C. So Gaussian elimination says that you can leave, that you make P. That you make your diagonal 1 and everything below it 0. And it doesn't care what all these other numbers are above your diagonal 1. This is called row echelon form. Row echelon form. And you don't necessarily have to remember that definition, row echelon form, or that name. As long as you know Gaussian elimination. And the other one I'm going to show you is called Gauss-Jordan. So Gaussian elimination uses row echelon form, which means you have your diagonal 1 with all the zeros below. Now in Gauss-Jordan, I'm going to write over here, you have your diagonal 1 with all zeros below and above. So that's the only difference in a different name here. So let me show you. Over here, this is called Gauss-Jordan. Gauss-Jordan elimination. And so we do all the same work, and like I said, the only thing that changes is what we do at the very end, and I can show you later what that is. So we wind up with our diagonal 1 with all zeros below and all zeros above. And having a hard time picking letters today. D, E, F. And so this is called reduced row echelon form. This is row echelon form. This is reduced row echelon form. So same wording basically. Reduced row echelon form. Alright. Gaussian elimination, Gauss-Jordan elimination. The only thing that's different is that you have zeros above your diagonal 1 over here. And that's really all you need to remember here. This row echelon and reduced row echelon is not super important. Just know the difference between Gaussian and Gauss-Jordan. Alright? What I prefer to use is Gaussian elimination. That's not necessarily saying that it's the easiest way, but for me, I don't care which way you end up doing it, but I'm just telling you in class here, I'm going to be doing this way most likely. But let's get into some examples. Alright, so the examples are going to be long and they're going to be big. And please bear with me while I'm using this board. I'll try to be as clear as I can. And this first example, I know some of you are still very shaky with what's going on. So I'm going to walk us through this example from beginning to end. I'm going to tell you the logic from each step and the logic I'm telling you you'll use on every single problem. so let me start by showing you how this will start. And I believe I've never wrote, I did example 1, so this is example 2. And what I have written here says solve using Gaussian elimination, which means row echelon form. But you don't have to know row echelon form. You just have to know Gaussian elimination. Gaussian means your diagonal one with zeros below. That's it. So we want to wind up there, and then everything after that point I'll show you how to solve it. So, but all I'm going to write here is solve, and here it is. 3x plus 7y minus 15z is equal to negative 12. X plus 2y minus 4z is equal to negative 3. Negative 4x minus 6y plus 15z is equal to 16. And I know this is a lot, but we're just going to take it a step at a time, and I'm going to erase the board probably 5 times the problem, but these will get easier. Alright, so what we want to do is we have our system of linear of equations here, and the first step is to write this in matrix form, and we want to make sure that all of our x's are lined up, all of our y's are lined up, all of our z's, and then our answers are all by themselves also. Alright, so they are. So we move on to the next step of writing this in matrix form. So what we have is 3, 7, negative 15, and negative 12. That's row 1. 3, 7, negative 15, negative 12. Is that big enough? Yeah. And then row 2 is 1, 2, negative 4, negative 3. And then row 3, negative 4, negative 6, 15, and 16. Alright. Now, I'm going to start, we're going to finish this problem to the very end, and we're going to solve for x, y, and z. And the x, y, and z that we find will satisfy all 3 of these equations. Meaning, we plug the same x, y, and z values in all 3 of these. This top equation equals negative 12, this one equals negative 3, and this one equals 16. And I've already told you what the first step is after we set up the matrix, and that is to get 1 in the top left corner. Think about what our end goal is. Our end goal is to get this diagonal 1. Our end goal is to get this diagonal 1 with zeros below it. So our first step is to always make this a 1. Once we make that 1, then we make everything below it 0. That's crucial to remember that, and I would encourage you to write down these steps as I say them on a separate sheet of paper somewhere if you want. So step 1, make the top left a 1, and then step 2 will be make everything below that 1 a 0, and so I'll say that many more times. All right, so to make this a 1 in the top left corner, what's the easiest way to do that? Think about it, pause it if you need to, go back and look at our 3 operations. This one's one of the simpler operations to do. I'll give you a second if you need to pause it. Alright, so we notice that we have a 1 right here. So we can interchange this row, this entire row, with this entire row. So that means interchange row 1 with row 2. So we have our long arrow, and I'm going to say row 1, interchange row 2. And it's important for you to write well, so I can follow along and you can follow along with what you did, and it helps you find mistakes. So you write your long arrow, and then on top of that long arrow you write the operation you're performing. Row 1, interchange row 2. So our new matrix and just go ahead and draw it. And then I like to write what's not changing. That seems to be very helpful for myself and other students I've found. Write what's not changing and then focus on what is changing. So row 3 is the only one not changing. -4, -6, 15, and 16. Alright, now row 1 and 2 are changing. Row 1 becomes, we're interchanging row 1 and row 2, so these are just flip-flopping. So row 1 is now 1, 2, -4, and -3. And row 2 is 3, 7, -15, and -12. Alright, so we made our first objective. Get 1 in the top left corner. Now, what did I say was the next step? Alright, our end goal is to have our diagonal 1 with zeros all below it. And just a side note here, whether you're doing Gaussian elimination or Gauss-Jordan elimination, you always have to get your diagonal 1 and zeros below first. So, just, that's a little side note. Alright, I'm going to take this matrix and going to come up here with it. So, like I said, bear with me and please let me know if that gets too confusing. But basically, I'm going to take this matrix and rewrite it up here. That's why some of these are going to get so long. On your paper, try to start here, draw your long arrow, and then your matrix, and then your long arrow, and then your matrix, and then try to come back down, long arrow, and your matrix. But so it makes sense for you up what I'm doing up here, I'm going to end up rewriting some of these multiple times. So I'm just copying this up here. And that's not enough room for me. Alright, now my next step is, so my first step was make the top left a 1, and now I want to make every entry below it in that same column. So I made this a 1, and every number below that 1 in the column, so this 3 and this -4, I want to make a 0. Alright, so take them step by step, one at a time. Let's focus on this 3. Let's make this 3 a 0. So when you're doing these, ask yourself, what do I need to add to this positive 3 to make it a 0? So 3 plus what equals 0? A -3. So what that means is I want to use this 1 that I just made up here to my advantage. So you can use this 1, you'll use this 1 in both of these examples, making this a 0 and this a 0. So I'll use row 1, multiply it by -3, and add it to row 2, and that will make this entry a 0. Alright? And eventually, the more of these you do, you'll catch on to what I'm saying. Just keep working at it. So here's my long arrow. And I want to multiply -3, -3 times row 1, add it to row 2, and that gives me a new row 2. Alright? If you're confused, we'll do more examples, so don't worry. Just for now, focus on doing these operations correctly, and you'll catch on soon. Alright, so this is similar to the example we did earlier, and I'm going to write it out here. So my final matrix, or my next matrix, is here. And which rows are not changing? See, 1 and 3 are not changing. So this is 1, 2, -4, -3, -4, -6, 15, and 16. So I just wrote what rows are not changing. And now we need to figure out row 2. Alright, so this says -3 times row 1 plus row 2. So -3 times row 1, which is a 1 here. So -3 times 1 is -3, and then plus row 2, which is a 3, and that's the entry. Add down gives you 0. So that is your new entry there. And that's exactly what we wanted to do. We made our 1 in the top left, and then we want to make everything below that 1 a 0. And then let's keep going. -3 times row 1. So -3 times 2 is 6. Add down, excuse me, it's -6. Add it to row 2 is 7. So when you add down to row Okay, so there's our matrix after our operation. And I'm sorry the video just cut out for a couple minutes, but it was only this portion here in blue, so I think you'll be okay. I hope. So now I'm going to just rewrite this over here. And after an example or two, I may stop rewriting it so much. But I just want to make sure you're really following along so far. Alright, so now we still are within our step 2 objective is to make everything below the 1 we just made a 0. So we made this 1 a 0 in step 1, and now we want to utilize this 1 to our advantage by making all the entries below it in that column a 0. So we did that to this entry. Now we need to do it to this -4. So ask yourself what. Well, first of all, if you think you're well enough off, go ahead and try to do this next step yourself. But I'm going to keep going. Ask yourself, what do we need to add to -4 to make it 0? In other words, -4 plus blank equals 0. That would be +4. So I need to multiply this row 1 by a +4, add it to row 3, and that gives me a new row 3. So what I mean is, I wrote that too big. So I'm going to kind of do this. Alright, so I said +4 times row 1, 4 times row 1, plus row 3 gives me a new row 3. I'm sorry, I know that looks terrible probably. It's a huge R. Alright, and just another little side note here. This is always going to be a plus. Do not make this a negative sign or a minus. You always have this as a plus. Alright? Just going to save you some headaches in the long run. Alright, so let's write our matrix over here, what we're going to. And what's not changing is row 1 and row 2. Alright, now I drew that kind of big, but that's okay. So now I'm doing 4 times row 1, adding it to row 3. 4 times row 1, so 4 times 1 is 4. Add down to row 3, which is negative 4. And that gives me 0. Alright, I'm going to write one more here. 4 times row 1 is 4 times 2 is 8. Add down to row 3, which is negative 6. And that gives you 2. Alright, and the rest I'll just do in my head. You write them out if you need to. Pause the video and try it. The more times you can pause it, the better off you're going to be. Alright, 4 times row 1. 4 times negative 4 is negative 16. Negative 16 plus 15 is negative 1. 4 times row 1. So 4 times negative 3 is negative 12. Add it to row 3. Negative 12 plus 16 is 4. Alright, I'm going to pause it and erase some so you don't have to sit here so long. Okay, so all I did was erase the top and I rewrote this up here so the next step looks clear. But let's talk about from here to here first. So did we meet our objective? We had our 1, 0, and 0. So now we're good. Alright, the next step is to move on to your next diagonal 1. Or the next diagonal, the next one in your diagonal. So you have this as your first one, and then you want to make this entry a 1, whatever that entry is. And it just so happens that it's already a 1. Alright, so that step is done. Okay, now we want to make everything below this 1 a 0. However many there are. There's only this entry. So now we want to utilize this 1 to our advantage that we just made. So we want to use this row, or this 1, to make this entry a 0. So 2 plus what is equal to 0? Negative 2. Alright, so that's where we come back up here. So we have our 1, the 0's below it, and then we want to make this entry a 1. But it's already done. So then that's one step we don't have to do now. Alright, so now we want to use this row to make this entry a 0. So I need to add negative 2 to this. So I need to multiply row 2 times negative 2 and add it to row 3. So negative 2 times row 2 plus row 3. And that's going to give me, whichever row I want changed, row 3. Alright, pause at any time if you want to try any of these. Alright, here's my matrix. And I want to write the rows that are not changing, which are rows 1 and 2. Alright, so now I'll do a little bit of side work here. Negative 2 times row 2 plus row 3. Negative 2 times row 2, so negative 2 times 0 is 0. Add down to row 3, which is 0, which equals 0, which is what we're looking for. We already made this 1, and this is 0, and this is 0. And we already made this a 1 also. So any work that we've done previously, any work that we've done on purpose, the 1, 0, and 0 here, we do not want those to change. If those ever change, you did something wrong, or you're doing it the long way. And you always want to backtrack and try to fix it because it will make it a nightmare for you to get back on track. Alright, negative 2 times row 2, so negative 2 times 1 is negative 2. Add down to row 3, which is 2. And then that gives you the 0, and which is what we're going for. And now the rest I'm going to just do in my head. Please write it out if you need to. Negative 2 times row 2, so negative 2 times negative 3 is positive 6. Positive 6 plus negative 1 is a 5. Positive 5. Negative 2 times row 2, so negative 2 times negative 3 is a positive 6. add it to 4, get you 10. Alright, so now we have that step completed. We have 1 in the top left entry, and we made all the zeros below it in that column. We made all the entries below it 0. Then we made this entry a 1, and we made all the entries below it in that column a 0. Now we have to move on to the next number 1 in the diagonal, which is here. Alright, so I'm going to rewrite this over here just so you can follow along. But while I'm doing that, work this. Try to figure out how to make that a 1. Alright, so now we have to go back and review your row operations, see if it will come out to you then. And if it does, pause the video and try to work it. I'm going to keep going. So I need to make this a 1. And the issue with this particular problem is you can't use either one of these rows. Because if you take, say, this row and you add it to this row, then you're doing 1 plus this 0, and you're changing work we've already done, and you don't want to do that. And same thing up here. If you take row 1 and add it to row 3, then that's an issue also, because you're taking this 1 and adding it to this 0, and it's changing this 0, and then this 2 would change this 0. So we're changing things we've already worked, and that's a no-no. That will get you in trouble. So we need a less obtrusive way of dealing with this. And if you go back and look at what we did on the row operations at the beginning of the lecture, and look at the number 2, and if that's a good enough hint, go ahead and pause and try it yourself. So what do we need to multiply to this 5 to make it a 1? Which also, if you look at the entire row, is a multiple of 5. So we can do 1/5 times row 3, giving you a new row 3. And this takes a little bit of time to get used to. Just think of it. Let's work it out. So let's rewrite our matrix first and write what's not changing, which is 1 and 2. Alright, and then, so negative, 1/5 times row 3. So 1/5 times 0, so 0 times 1/5 is equal to 0. Anything times 0 is always 0. And then 1/5 times row 3, which means 1/5 times 0 again, which is just 0. Which that's exactly what we wanted. We don't want any work that we've done already to change. And now we have 1/5 times row 3, so we move to the next one, which is 5. So you have 5 times 1/5, which is 5 divided by 5, and that's equal to 1. And then 1/5 times 10, which is 10 divided by 5, which is 2. And that is row echelon form. This is where Gaussian elimination differs from Gauss-Jordan. This is where they diverge, I guess you could say. Here when we're doing Gaussian elimination, we stop here and then we solve for x, y, and z. If we were doing Gauss-Jordan, we would continue in matrix form in making these a 0. I find it to be a little more shorthand if we just go ahead and do Gaussian elimination instead of Gauss-Jordan. So that's why I prefer it. Alright, so what's the best way to do this here? Alright, I'm going to do this a little different than what I would want, but this is what I've got to work with. So remember, this was, when you write these are the coefficients of each variable, and these are the answers. And this was equation 1, equation 2, and equation 3. So everything in this column, these were the x values, these were the y's, z's, and all of these were that equals the answer over there. So now we can convert these into other equations, into equations like they were in the beginning. So alright, so the easiest way to start these is to start with the bottom, because there's less to deal with. So this means that there are 0 x's, 0 y's, and 1 z. That's equal to 2. So this bottom row out pops the answer for z. Z is equal to 2. Alright. And typically if I had a bigger board, I would keep working out this way. So I would say, so I'm just telling you to do it this way, but I'm going to go this way, unfortunately. But this is telling you that there's 0 x's, 1 y, minus 3z is equal to negative 3. But I'm going to work out this way. Alright, 0 x's, 1 y, and then minus 3 times z is equal to negative 3. Alright, so ask yourself, how can we simplify this drastically? Do we know what y is, or do we know what z is? Yeah, we know what z is because we just wrote it over here. Z is 2. So I can replace this z with 2. Y minus 3 times 2 is equal to negative 3. And just simplify. Y minus 6 is equal to negative 3. Add the 6 over, so y is equal to 3. Alright, and we are almost done. One more to go. Now you take this row, and again, normally I come out this way because it just makes more sense, but alright, so this is telling you you have 1x, 2 y's, minus 4 z's is equal to negative 3. So 1x plus 2y minus 4z is equal to minus 3. And here we don't know x, but we know y and we know z. So we just plug those in and out pops the x. So x plus 2 times y, which is 3, minus 4z, which we found z to be 2, and that's equal to negative 3. And then it's simplifying. X plus 6 minus 8 is equal to negative 3. So this 6 minus 8 is x minus 2 is equal to negative 3. Add 2 to both sides, so x is equal to negative 1. Alright, and the way you write your final answer is like this. Let me put this down. You would write it something with these squiggly lines, and it's a point now. It's in 3 dimensions. Negative 1, x, y, and then z. Alright, so this point represents the intersection of those 3 equations at the very beginning. Alright, we'll do some more examples. Okay, so let's look at another example. This time, I want you to try to work it. I'm going to do a smaller example, shorter example. The only thing that's going to be different is that I'll write it and show you what's going to be different here. I'm going to help you with the first step or two, but then I want you to take off with it. Example 3, I believe. And my notes say solve using Gauss-Jordan, which is get zeros below and above. But do whatever way you want. It's fine. I'm happy either way. So solve x equals 17 minus 2y, and then 3 times x plus 2y is equal to 47 minus y. Alright, so this is obviously different than what we just did. And I kind of told you already that we need to make sure that all the x's are lined up, all the y's, and all the equal signs. And there's nothing else on the equal sign except for, the answer. So here we have that issue of we need to rewrite this so that it makes a little more sense when we put it in matrix form. So this top equation, we can just add 2y to both sides, and that fixes that one. That one's pretty easy. And then this second equation takes a little more work. So we need to distribute this 3 in here. Let's do that first. So 3x plus 6y is equal to 47 minus y. Now we need to get all the x and y's over to the left and make sure they're lined up. So add y to both sides. So you get 3x plus 7y is equal to 47. Alright, so now we have successfully rewritten these two equations. And just so it kind of pops out easier, I'll go ahead and rewrite them together so we know what we're doing. So this, I'll just circle them. It's this one and this one. Those are our equations that we need to solve. So now we can put these in matrix form. And go ahead and pause the video, and I'd like you to try this yourself. Alright, so we have a 2 by 2, 1, 2, 17, 3, 7, 47. And so our first objective is to make this top left entry a 1. And it just so happens it already is, so job well done. Now that when we have a 1 in the top left corner, we want to make all the entries in that column below it a 0. This is the only entry, so we need to make this a 0 somehow by adding, what do we need to add to positive 3 to make it 0? We need to add a negative 3. So we need to multiply this row by negative 3 and add it to row 2. So negative 3 times row 1 plus row 2 implies a new row 2. Alright, and this may be the last example I do this little side work here. So negative 3 times row 1, negative 3 times 1 is negative 3. Add to row 2, which is a 3. That gives you 0. Alright, I should have drew my matrix first. Thanks for reminding me. Alright, so what's not changing is row 1. And I just found my first entry to be 0. Alright, negative 3 times row 1, negative 3 times 2 is negative 6. Add down to row 2, which is 7. That gives me 1. Alright, and then negative 3 times row 1, which is negative 3 times 17. And that gives you 34, 51, negative 51, plus 47, and that gives you negative 5. Did I do that right? I think I messed up. Yeah, because that's not 5, it's 4. Negative 4. That's what I need y'all here for. Alright, now here's my matrix after I apply this operation. So I needed 1 in the top left corner. I had it. Now I wanted to make a 0 in the bottom left corner. Now I did that, or below it. Now I need to move on to my diagonal and make this a 1, but it is already. So now I can stop and do Gaussian elimination. which is how we did it in the last example. Or you can continue on and do Gauss-Jordan. And I'll do Gauss-Jordan on this one example, just because it's shorter, a short example, and it might be a little shorter on this example, but just so you have seen one, I'm going to show you here. So remember, Gaussian elimination is what we did in the previous example, where you make the diagonal one with zeros below it. Gauss-Jordan, you make the diagonal one with zeros below and above. So go ahead and try to pause the video if you think you can do it. Alright, so there's the problem matrix. And now I need to make this entry a 0. So I need to use this row, a multiple of this row, and add it to row 1. So what do I need to add to 2 to make it a 0? Negative 2. So I multiply negative 2 times row 2 and add it to row 1. Negative 2 times row 2 plus row 1 gives you a new row 1. And the only time that you will use a bottom row to update a top row is if you're using Gauss-Jordan, which I don't typically recommend very much to use. So unless you're super okay with this and super familiar, I would just stick with Gaussian elimination, the last example we did. Alright, so my matrix now will be this. I'm not changing row 2, 0, 1, negative 4. Alright, but I'm doing negative 2 times row 2. So negative 2 times 0 is 0. Add it to 1 is still 1. So again, we didn't change work we already had done, so that means we're doing something right so far. And if I did end up changing this 1 somehow, that means I did it wrong. I need to backtrack. Alright, negative 2 times row 2. So negative 2 times 1 is negative 2. Add it to positive 2 gives you 0. And then negative 2 times negative 4. I wouldn't say easier, but more likable, is it just pops out your answers for you. So start at the bottom like always. This is 0x, 1y is equal to negative 4. So that says y is equal to negative 4. Up here this says 1x plus 0y's is equal to 25. So x is equal. Coming up here on example 4, I found a mistake halfway through the problem. I corrected it, and it shouldn't affect too much, and you may catch it, and it won't affect you really at all while you're working the problem. I wrote positive 22 is equal to positive 22 on one of the equations, and when I converted it to matrix form, I wrote negative 22. But I fixed it along the way, and it shouldn't affect you too much. Just know that that's coming up in this problem. Okay, I'm going to do another example. This is going to be a 3x3 matrix, and this is a good representative of something you might see on the exam. So I'm going to ask you to work it yourself. I want you to pause it at the beginning. I'm just going to go through and work it. I'll talk as I do it, but I may go a little faster just because I want you to really work it yourself, and don't forget about the homework out there. So I think I'm on example 4, and I'm going to say solve. And I'm going to solve using Gaussian. But if I just say solve on the test, you can solve however you like. Solve 2x minus 5y minus 21z is equal to 39. And then x minus 3y minus 10z is equal to 22. And then x plus 3y plus 2z is equal to negative 8. And I'm going to go ahead and give you the answer now so you can check. That way you know if you got it right. And I encourage you, if you do get it wrong, to go back and try to fix it yourself before you watch me. But I'm going to leave you to your best judgment. When you do this, you're going to get 7, negative 5, and 0. Alright? So pause it, try to do it yourself, and only use me if absolutely necessary. Okay, so the first step is we need to write this in matrix form. I'm going to try to fit it in here. 2, negative 5, negative 21, 39. 1, negative 3, negative 10, negative 22. I didn't leave myself enough room here. Make sure I wrote that right. 2, negative 5, 21, 3. Okay, so my first step is I need to make this top left a 1. So here I have both of these as a 1. I'm just going to take row 2 and interchange with row 1. Row 1, interchange row 2. Alright. So the row that's not changing is row 3. And 1, 3, 2, negative 8, 2, negative 5, negative 21, 39. Okay, I messed up here. I accidentally wrote the wrong row right there. That should have been 1, negative 3, negative 10, and negative 22. There we go. Gotta be careful, alright? I make mistakes too, so you just have to be careful and go back and look through where your mistake was. So now the next step is to make this a 0. This 2 is 0. So I'm just going to rewrite real quick. Alright. To make this 2 a 0, I need to add negative 2 to it. So I'm going to use row 1 times negative 2 and add it to row 2 to give me my 0. Now some of you may see that you could use row 3, but don't do that. What you want to do is you always want to use the 1 in the diagonal that you made. So use the 1 in the diagonal above it to make it a 0s below. Alright, so to make this a 0, I need to do negative 2 times negative 2 times row 1 plus row 2 gives me a new row 2. And so my matrix over here, let's write what's not changing first, which is row 1 and row 3. 1. Alright, so that's not changing. I'm going to skip writing all of the intermediate steps here. So negative 2 times row 1 plus row 2. Negative 2 times 1 is negative 2. Negative 2 plus 2 is 0. Negative 2 times negative 3 is positive 6. Positive 6 plus negative 5 is 1. Negative 2 times negative 10 is positive 20. Positive 20 plus negative 21 is negative 1. Negative 2 times negative 22 is positive 44. Positive 44 plus 39. I think I did something wrong. Okay, this shouldn't have been negative here. It's negative 22. If I wrote that previously, then just go back and erase those. I am so sorry. Alright, so this should be a positive there. Alright, so negative 2 times positive 22 is negative 44. Negative 44 plus 39 is minus 5. There we go. Alright, like I said, I'm prone to mistakes on these two. They're big and they take a little while, so just be careful. Alright, so from here, this matrix up here, now I have my 1 and 0. I need to make this a 0 also. So I'm not going to rewrite it like I've usually been doing. So I need to add a negative 1 here. And so let's do it like this. I'm just going to write my long arrow here, and I'm going to write my new matrix over here on the bottom left. So I need to do negative 1 times row 1 and add it to row 3. Negative 1 times row 1 plus row 3 is a new row 3. Alright, and so what we get is, I'm going to write what's not changing, which is rows 1 and 2. Alright, so negative 1 times 1 is a negative 1. Added to row 1 is a 0. Negative 1 times negative 3 is a positive 3. Added to 3 gives you 6. Negative 3 times negative 10 is a positive 11. Positive 10, excuse me. Added to 2 gives you 12. And then negative 1 times 22 is negative 22. Add it to negative 8 is negative 30. Alright. Now we made our 1, 0, 0 like we had wanted. So once we make our last entry 0, we move on to the next one in our diagonal and we make this a 1. It's already a 1, so we're good to go. Now we need to make a 0 below there. So how do I make this a 0? What do I need to add to 6 to make it 0? I need to add negative 6. So I'm going to do negative 6 times row 2, add it to row 3. Negative 6 times row 2 plus row 3 gives me a new row 3. And let's draw our matrix and write what's not changing. So 1 and 3 are not changing. Alright. And so let's do this. Negative 6 times 0 is 0. Add it to 0 gives you 0. That's what we're wanting. We don't want to change any work we've already done. Negative 6 times 1 is negative 6. Add it to 6 gives you 0, which is what we were wanting. Negative 6 times negative 1 is positive 6. Add it to 12 is 18. Negative 6 times negative 5 is positive 30. Add it to negative 30 gives you 0. Alright, and that's okay. It's no issue having the 0 over here. Alright. Now, we're getting closer here. I am going to rewrite the equation. I'm going to pause it. Okay. So now, we have our 1, 0, 0, our 1, 0. Now we need to make this last entry a 1 to finish out our diagonal. Alright. So we don't, we can't add either of these columns to this row. We can't add either of these rows to row 3 because we're going to change these zeros if we do that. So we need to think back to the second row operation again. And that one's very helpful. We can multiply this row 3 times 1/18 and make this a 1. So 1/18 times row 3 gives me a new row 3. Alright. So let's write what's not changing, which are rows 1 and 2. Alright. And now multiplying every entry in row 3 by 1/18. 1/18 times 0 is 0, so that doesn't change. 1/18 times 0 is 0, so we didn't change any work we've already done. 1/18 times 18, which means 18 divided by 18, that's 1. And then 1/18 times 0 is 0. And now we're here in Gaussian elimination. And I encourage you to pause and try to work it. Alright, so this entry here, always start with the bottom and work up. These are your x's, y's, and z's. 0x, 0y, and 1z. So z is equal to 0. Next, let's work on this equation. 0x's, 1y, minus z is equal to -5. Alright, we know what z is, it's 0. So we plug in 0 here for z. We know this, we plug it in there. So we get y minus 0 is equal to -5. So y is equal to -5. And then almost done. We work this equation. We get 1x minus 3y minus 10z is equal to 22. X minus 3y, we found y to be -5. 3 times -5 minus, this should be 10z, excuse me. 10 times 0 is 22. So x negative, this becomes positive 15. This is minus 0, which is equal to 22. And so we need to subtract 15 from both sides. So x is equal to 7. And our answer is 7, -5, 0.